Hello.
Srinivas sir,
Yes, sir.
sir, let's wait for another 5 minutes so that the students will join.
Yeah, yeah, sure.
Okay, sir.
Obviously.
Dear students and colleagues, a very good afternoon to you all. Thank you very much for joining this talk, and I formally welcome you all. So we are all here to attend this expert talk on From Basics to Applications, a deep dive into matrix algebra and computational methods. It is with great pleasure and enthusiasm that I take the opportunity to briefly share you the purpose of initiating this expert talk. As you know, at SR University, we are offering an elective course with the title Matrix Algebra and Computational Methods to BTech first year students. As we are about to conclude the semester in a few days, this talk unravels the intricacies of the concepts of matrix algebra and computational methods by unlocking the insights that transcend the boundaries. So this talk also creates an overview with tangible applications which will help you to perform well in upcoming examinations. Keeping this in view, throughout this webinar, we will delve deep into the fundamentals as well as applications associated with the concepts of matrix algebra and computational methods. So we are honored to be joined by esteemed speaker and educator, Dr. Srinivas Rao Garu, who will share his invaluable insights, experiences, and expertise on this subject. And you see later in the, or else during the talk, if you have any queries, or if you wanted to know anything else, you can post your questions in the chat box so that we'll convey those questions to the speaker, right? So please keep that in mind. You're not allowed to unmute yourselves. So if you have any questions, you are supposed to post your questions in the chat box. Now, let me take the privilege to invite my colleague, Dr. B. Ravinder, to introduce today's guest. Ravinder, sir.
Yeah, good afternoon, one and all. So it's my pleasure to invite today's expert talk by Srinivas Rao. So first of all, I will give brief introduction about Dr. Srinivas Rao. So Professor Srinivas Rao completed his MSc in mathematics from Indian Institute of Technology, Madras, India, and PhD in mathematics from Motilal Nehru National Institute of Technology, Allahabad, India. So Tota's areas of interest, research interest are computational algebra, numerical analysis, and mathematical modeling. He has published more than 50 research papers in several international journals and presented his work in different national and international conferences as oral presenter and expertise invited speaker. He is also editorial board member of various international journals and received several awards on academic research work. Presently, he is working as associate professor at the Department of Mathematics, Amrita Vishwavidyapeetham, Amaravati, India. So this is a short or brief introduction about Srinivas Rao. So please go ahead.
So may I start, sir?
Yes, sir. Please go ahead.
Yeah. Before going to, I want to share my screen. Is it visible to all?
Yes, sir. It's fine.
So before going to start, I would like to thank organizers for giving me this opportunity, inviting me and giving this opportunity to present my work, means my knowledge to share with the students. In this talk, we are going to focus on matrix algebra and computational methods. Presently, as Ravindra Sir told, presently I am working as Associate Professor of Mathematics at Amrita Vishwavidyapeetham, Amaravati campus. The outline of the talk is as follows. It is divided into two modules. Module 1 consisting of matrices, linear equations, and a brief introduction to linear algebra. Module 2 consisting of numerical methods to solve initial value problems, the differentiation and integration, and to find approximate solutions of transcendental equation also. Is it audible?
Yes, sir. It's fine, sir.
Something. So module 1, matrices and linear equations. Start with the basic definitions of matrices, and which you already know. Just I am recalling once again various types of matrices. Row matrices, row matrix which consisting of only single row. Column matrix which consisting of single column. Null matrix or a zero matrix consisting of all zeros in the entries of matrix. Square matrix, that is a number of rows is equal to number of columns. So that we call it as a square matrix. Otherwise, we call it as a rectangular matrix. Diagonal matrix consisting of all zeros except diagonal values. Scalar matrix consisting of all zeros except diagonal, and that is a fixed value, some scalar value. And the unit matrix or identity matrix, where the identity their principal diagonal consisting of only one, and all other elements of matrix should be zero. And the matrix symmetric matrix, A transpose is equal to A transpose. It is already defined in point K. However, briefly recalling, transpose is nothing but if you interchange the rows and columns, the matrix remains same. It will not be changed, so that then matrix we call it a symmetric matrix. So changing this process, rows into columns, we call it as a transpose of the matrix. Even after changing rows into columns and the matrix remains unchanged, then that is that we call it as a symmetric matrix. And a skew symmetric matrix is A transpose is equal to minus A. Triangular matrix is divided into two parts. One is upper triangular matrix, lower triangular matrix. And upper triangular matrix consisting of all non-zeros above the diagonal and the zeros below the diagonal. And the lower triangular matrix consisting of all zeros above the diagonal matrix and below diagonal non-zeros. And transpose of a matrix, so that is just interchanging rows and columns. So A is given and A transpose is simply changing the rows into columns. And the conjugate of a matrix is like a conjugate of a number, complex numbers. We simply change the sign of the complex variable. So here 1 plus I can be conjugate will be 1 minus I. Similarly, conjugate of matrix A is denoted by A bar. A bar is equal to each component consisting of complex entry, that conjugate we take. So we can see simple example, conjugate of a matrix A bar and A power theta. Transpose of a conjugate matrix A denoted by A power theta. So which is consisting of A bar and a transpose. Both are same, either A transpose or a bar or A bar transpose. Both are same only here. Either we can take transpose first and then take a conjugate, or maybe you can take first a conjugate and then take transpose. Both will be remain same, that is A power theta. And Hermitian matrix, it is like a skew matrix. There we have A is equal to A transpose. Here Hermitian matrix we have A is equal to A power theta. Similarly, skew Hermitian matrix consisting of A is equal to minus A power theta, or A power theta is equal to minus A. It is like a skew symmetric matrix. There we have A transpose is equal to minus A. Here we have A power theta is equal to minus A. Idempotent matrix, that is equal to A square is equal to A. In general, normally when you discuss about linear algebra, there we will discuss about idempotent elements. There A square is equal to A, we discuss about that. Similar to that one, we have idempotent matrix here. A square is equal to A. If matrix A is given, if you multiply A with itself, remains same. Will not be changing the entries of the matrix. So A square is equal to A. Such matrix we call it as idempotent matrix. Periodic matrix, it is like a periodic function which we already know in terms of functions. F of x plus t is equal to f of x, where t is a period of the function. Similarly here, periodic matrix is nothing but a power k plus 1 is equal to a, where k we call it as a period. So if you multiply a into up to k plus 1, it remains same. So here k we set it to be period of the matrix A. So if you choose k is equal to 1, then we will get a square is equal to a, then it will be converting into idempotent matrix, which you have already seen in our previous slide. Nilpotent matrix is nothing but a power k is equal to 0. So here we are going to find the value of k where a power k becomes 0. So that k we call it as index of the nilpotent matrix. Suppose if your matrix is given, look at your example already given, a is equal to ab, b square minus a square minus a. If you find a square, so that will giving 0, 0, 0. So a square is equal to 0 we are getting. As per definition, a power k is equal to 0, where k is equal to 2. So index will be 2 in this case. Inverted matrix, that is a square is equal to I. Idempotent we already seen, a square is equal to a. Similar to that one, invalidatory matrix, a square is equal to I. Instead of a, you will get identity matrix here. A square is equal to I, and I square is equal to I, it is always true. So that is a inverted matrix. And a square is equal to I, if you are able to find that matrix, we call it as an inverted matrix. Equal matrices that we already know, two numbers are equal, both are same. Similarly, equal matrices are each entry of two matrices should be identical. So that is A and B are given. You can see each component, if you compare, both are same. So we say that A and B are same. Singular matrix or singular matrix is nothing but whose determinant is equal to 0. If determinant is not equal to 0, we call it as non-singular matrix, or maybe call it as a regular matrix also. Regular matrix and singular matrix here. Singular matrix is determinant is equal to 0. Regular matrix is determinant is not equal to 0, or non-singular also we can say. And the matrix operation, this is also simply recall, we already know addition, subtraction, division, and all those things we will do. Addition of two matrices, A and B are given, and A plus B is simply obtained by component-wise addition. A is given a matrix you can see here, and B also given. A plus B is component-wise, 4 plus 1, 2 plus 0, 5 plus 2, and so on. This is elementary things, however, I'm just recalling once again. And subtraction also similar to addition. A is given, B is given, A minus B is component-wise subtraction here, 8 minus 3, 6 minus 5, 4 minus 1, and so on, component-wise, and the resultant matrix will give A minus B. And the multiplication is a little bit different here, even though you already studied in elementary school. Just I'm recalling once again, to find a multiplication of two matrices A and B, we simply take first row of matrix A and first column of matrix B, and we simply take dot product of these two, and we will get a first element of the resultant product. So that we already know this thing. However, I'm just verbally saying that one. And if two matrices are given, I think everyone can able to find matrix A into B. Some properties are given here, and matrix product is not commutative always. A into B is not always B into A. You can find a lot of examples that AB is not equal to BA. However, if you able to find AB is equal to BA, doesn't implies that it is always true. So we can find a lot of examples that not satisfying this commutative law, that is AB is BA. So hence it is not a commutative law, not satisfying commutative law. Matrix multiplication is associative. That is A into BC is equal to AB into C. That will satisfy easily. And matrix multiplication is distributed with respect to addition is also true. A into B plus C become AB into AC. And A into I is equal to I into A is equal to a multiplication of matrix A by unit matrix. That is also well known. Identity matrix into any matrix that will give same matrix. A into I is equal to I into A is equal to A. Multiplicate inverse of a matrix if determinant is not equal to 0. This is also already familiar. To find inverse of a matrix, that should be a non-singular matrix. That is, determinant should not be equal to 0. If determinant is equal to 0, then we cannot able to find, because the inverse matrix formula we already know, adjoint A divided by dta. So when dta becomes 0, then we cannot able to find A inverse. Hence, we take here multiply inverse only when determinant is not equal to 0. So that also given here, A into A inverse is equal to A inverse into A is equal to identity matrix. If A is a square matrix, then we can find A power n. So A power n, in general, we have A into A into A into up to n times. So if you take particularly A square can be calculated A into A, and A cube can be calculated A into A, and so on. We can generalize to up to n. And in particular, if you take the power is 0, A power 0, that will be giving identity matrix. In general, if you take any scalar quantity, any 2 power 0, 5 power 0 will be 1. Similar to that, any matrix power 0, that will be always identity matrix. And I power n is equal to I also. It is also like a similarly scalar case. If you take 1 power 100 is equal to 1, 1 power 2 is equal to 1, 1 power 10 is equal to, like that. Identity matrix for any number is always identity matrix. Elementary transformations. Here, normally we have two type of transformations are there, elementary transform. One is row transformations, another one is column transformation. Based on the requirement, we use to take row transformations or column transformations. So this will be in general applicable for both ways, but I'm discussing with the only row column, and it is already mentioned in the bracket also or columns also. Interchange of any two rows is possible in elementary transformation. Not only rows, even columns also. Interchange of two columns and the multiplication of the element of row by non-zero scalar. Suppose you can multiply second row with 5 or third row with -1 or sixth row with 1/2, something like that. You can multiply scalar of any row. Addition of constant multiplying of element of any row to the corresponding element of the other row. That is, it is already given Ri plus k into Rg. Second row plus 5 times of third row. We can do like that. And the same operations can also be followed to columns also, column rows also. Not to Ci plus k into Cj. That also second column plus 2 times of third column. That also be applicable. So based on the requirement, we will take row operations and column operations, or together also we can take. That we will see that I will explain where we are going to take row operations and the column operations and together where we are going. Two matrices are said to be equivalent. Normally we denote with A is equivalent to B. A is equivalent, that is, if you apply row transformations or column transformation or both, A is converting into some other matrix. So these first matrix and after conversion of the matrix, that both we call it as a equivalent matrices, and it is denoted by A tilde B. And using these elementary matrices, we can find the inverse of a matrix easily, very instead of taking the standard formula adjoint A divided by det A. So here we already know A can be written as I into A. It is like a in scalar case, 2 is equal to 1 into 2, like that. Matrix A is equal to 1 into identity matrix into A. And we take left hand side matrix, given matrix, and right hand side we multiply I with the given matrix. That will be remain same. A is equal to A only. And we apply these elementary operations on left hand side, and whatever operations we apply for matrix A, same operation we apply for identity matrix also. And we keep on doing this until we get a left hand side identity matrix. Then the right hand side identity matrix converting into non-identity matrix. That suppose if you denote with P, then in that case P into A on right hand side and the left hand side become I. So P into A is equal to I. That implies A is equal to, we get our P is equal to A inverse. So inverse can be calculated simply by applying elementary operations. For example, if you look at this one, A is given 0, 1, 2, 1, 2, 3, 3, 1, 1. So applying row operations here, we already, I think we already know how to apply, because these are already discussed by your expert teacher. So given already operations also given here. And initially left hand side we have A, and right hand side identity matrix into A. In a second we can see after the elementary row operation in a equation. So left hand side A is equal to I into A, and we apply some operation, row operation, and it is converting that left hand side into identity matrix, and right hand side P into A. That second line from bottom, I is equal to PA implies P is equal to A inverse. So I is equal to left hand side identity matrix, it is already converted, and P is equal to 1/2 minus 1/2, 1/2, and so on, and A is remains same. Now some matrix into A is equal to identity matrix, then A can be written as, or P is equal to, we take other side, that will be A inverse. Moreover, we can also cross check this also. If you multiply matrix P and A, you will get identity matrix. Hence, we say that if AB is equal to I, then A can be written as B inverse. So this is one way to find identity inverse of a matrix by converting a right hand side into identity matrix. And by using row operations, we can also calculate the rank of the matrix. The rank of the matrix is very simple. If you apply row operations, the number of non-zero rows after converting into echelon, we normally call it as echelon form. Converting into echelon form, the number of non-zero rows will be the rank of the matrix. And at the same time, we can also apply column operations. As I said earlier, we can apply either row operation, column operation, or together also you can apply. If you apply together row operation, column operations, then the matrix is converting into some identity matrix. Identity means not complete identity matrix. Some entire rows and some entire columns become zeros. The remaining non-zero terms become as identity. Here we can see PAQ is equal to IR 0, 0, 0. I means your identity of order R. the remaining rows will be 0. This R we call it as a rank of the matrix. Or if you want to apply only row operations, then it will be converting into echelon form. The number of non-zero rows in the echelon form, that will be the rank of the matrix. You can see example also given. A is given here 4 by 4 matrix. We apply elementary row operations and converting this into some make it zeros from bottom as many rows as possible. And at the last, we can see that entire row becomes 0 and row 1, 2, 3 are non-zero rows. At least one number is there. If we say that that is non-zero row. If entire row is 0 means all elements of the row should be 0. So fourth row of last matrix is 0, 0, 0. So except that one, the remaining 3 rows are there which are non-zeros. We call it as rank of that. The number of non-zero rows will be the rank of the matrix. So A is given 4 by 4 matrix and the rank of that matrix will be in this case 3 because there are 3 non-zero rows. And how to apply these operations and all those things, there is algorithm. We follow the algorithm. Briefly, I will explain here. First element we take, the first element of the matrix, that 1 comma 1 element, the matrix. Using that one, we make all zeros below that one, and take 2 comma 2 element and make zeros below that one, and take 3 comma 3 element and make zeros. All of this in this process, sometimes the entire row becomes 0. So like it is happening here, they follow the procedure. First 1 comma 1 element they took and make zeros below that one, and the 2 comma 2 element they took, they make zeros below that one. 3 comma 3 make element, and automatically the fourth element also becomes 0. 4 comma 4 element. So in that case, the fourth row entirely 0. So there are 3 non-zero rows. So rank will be 0. This is the fixed algorithm. If you are more interested, we can search in Google. Not only that, if you are familiar with Python or any other programming language, you can create your own algorithm to find a rank of the matrix. Taking in general, you take n by n matrix, not only 4 by 4 matrix. You can take n by n matrix. Based on the input, you will apply the operation. So first, this algorithm is more important and simple also, elementary algorithm in mathematics to find the rank of the matrix. And using these row operations, we can also solve a system of simultaneous equations. The process is very, very simple. We convert a given system of equations into matrix notation, and using rank of the matrix, then we will decide whether it has a solution or not. If it is a solution, then we will find that solution. So here there are two possibilities only. So when system of equations are given, we have to decide whether it has a solution or not. If solution is there, then we call it as a consistent system. If there is no solution, then we say it is inconsistent system. When it is inconsistent means no solution. So no further discussion after that, because when there is no solution, we will not investigate anything after that. But the first case, when it is a consistent system, that means that there is a solution. In that case, we have to do further investigation whether it has a unique solution or infinitely many solutions. If it is a unique solution, how can you find unique solution? If it has infinitely many solutions, then how can you find infinitely many solutions? So that is the case when we have consistent system. So first we convert a given system of equations into matrix notation, and we take a coefficient matrix A on the right hand side matrix B. Together we call it as the augment matrix. You can see on the slide that is mentioning inside the box, AB is equal to C. The C we call it as the augment matrix. So A and B, two matrices, the coefficient matrices are together we write as a one matrix, denote with C. And based on the rank of these matrices, we will decide whether it has a solution or not. Or if it is solution, then how many solutions are there, whether it has a unique solution or infinitely many solutions, that can be calculated. This is also one of the algorithms you can easily implement any programming language, either MATLAB or Python or Java, anywhere where. So first we system of equations will be given. We take coefficient matrix A comma B and check find the rank of the matrix as we discussed last time in previous slide, that algorithm how to find convert the echelon form. Converting into echelon form, based on that we will find the rank. So if rank of A is equal to rank of C, where rank of C means augment matrix. If rank of A is equal to rank of augment matrix, then it is consistent. That means there is a solution. If there is a solution, then we have to check whether it is unique solution or infinitely many solution. So rank of A is equal to rank of C, that is also equal to n, that number of unknowns. Suppose there are x, y only. If rank of A is 2 and rank of C is 2 and 2, then the number of unknowns, so x comma y also 2, then there is unique solution. And infinitely many solution, if rank of A is equal to rank of C and R is less than n. Suppose there are three unknowns x, y, z, and three equations are given, and rank is equal to 2. Rank of A is equal to 2. Rank of argument matrix also 2. But there are three unknowns, which is less than 3. R is less than 3. In that case, there will be infinitely many solutions. And the last case, if rank of A is not matching with rank of C, then we say that in consistent system, that is, there is no solution. When there is no solution, then we will go for numerical methods. So that is in second part that we will discuss later, how to solve the inconsistent system by using numerical methods. In brief, a system of non-homogeneous linear equation is represented by Ax equal to B. When B is equal to 0 in particular, we call it as a homogeneous linear system. That we will discuss coming 2-3 slides. First, we focus on the non-homogeneous linear equation. Ax is equal to B. So based on the rank, we will decide whether it has a solution or not. First, we find a rank of A and a rank of argument matrix. If rank of A is not equal to rank of argument matrix C, then no solution. After that, no further integration. We stop there. But if it is rank of A is equal to rank of C, then solution exists. When solution exists, then we have to check whether it is unique solution or infinitely many solution. So rank of A is equal to rank of C is equal to n, then unique solution. Rank of A is equal to rank of C less than n, then infinitely many solutions. This is in brief about the system of non-homogeneous equation. So simple example is given. Intentionally, I given here 4 equations and 3 unknowns. So we convert this into matrix notation. The coefficient matrix A is simply collect the x1, x2, x3 coefficient 1, 2, minus 1, and right hand side 3 is there. It's separated by dot, like A comma B we denote as a C. You can see the augment matrix C is equal to A comma B, where A is the left hand side coefficient matrix and B is the right hand side after equal. So those are we can represent here. And we apply row operations as we did in the echelon form. We do the process and we make as many zeros as from the bottom. And we can see last here, before rank of C is equal to 3, we can see entire 4th row entirely 0. And there are 3 non-zero rows, so rank will be 3 in this case. And if you consider only before the dot, that is matrix A. And there are again the 4th row entirely 0. The rank of A will be remains 3 only. And here number of unknowns will be 3 again, x1, x2, x3 only there are. Even though there are 4 equations, but x1, x2, x3 only are there. So rank of A is equal to rank of C, and that is also equal to 3 number of unknowns. So there will be unique solution that can be solved very easily from bottom last equation 0, 0, 0 equal to 0. That is satisfied. So we can ignore because all of them are zeros. The other one is 0, 0, 5 by 7, 20 by 7. So 0 into x1 plus 0 into x2 plus 5 by 7 into x3 is equal to 20 by 7. So 0, 0 first 2 terms and x3 terms can be calculated from last part 1 row. 5 by 7 into x3 is equal to 20 by 7. Terms will get cancelled. x3 is equal to, you can calculate. And we substitute this x3 in second row. 0 into x1 minus 7 into x2 plus 5 into x3 is equal to minus 8. And x3 we already calculated and x2 can be calculated. From first equation, x1 can be easily calculated because we already know x2 and x3. Therefore, we have x1 is equal to minus 1, x2 is equal to 4, and x3 is equal to 4. So unique solution is there because the rank of A is equal to rank of C is equal to 3 number of unknowns. Now come to the homogeneous equation where B is equal to 0. So here we have only one option. There we have two options when B is not equal to 0, homogeneous system. Non-homogeneous system, we have two options. Either it has a solution or no solution. If no solution, no option, but solution, infinitely many solution or unique solution. But here we don't have that many options. We have only one option, that it has always solution. There is always a solution. There is no concept of no solution. There will be always solution when homogeneous equation. So when there is always solution, we have to decide only that whether it has a unique solution or infinitely solution. Unique solution means again it is a trivial solution. That is 0, 0, 0 is only the solution. And that we call it as a trivial solution. Either it is a trivial solution or unique solution or infinitely many solutions. Same thing we can follow the up there. Right hand side becomes B is equal to 0. If you take it as augment matrix, then A comma B is equal to C if you denote. So A comma 0 is equal to C. We can apply the same technique here also. But instead of doing that much, we can shortcut this one. Simply find the determinant of the matrix A. Based on that, we will decide. If rank of A is equal to 0, then determinant of A is not equal to 0. When determinant of not equal to 0, then there is a trivial solution, that is 0, 0, 0. If determinant of A is equal to 0, then there will be infinitely many solutions. So that solution can be calculated similar to previous. So here, if you take each column of the matrix, we denoted with each x1, x2, x3 as a vectors. Vectors are column matrix. Normally, both are same vectors or column matrix. We denote x1, x2, and so on, xn. And based on this, rank also will decide this one based on this one. If all these vectors are independent, x1, x2, and so on, xn, then if you make it as a matrix, first column, second column, and so on, nth column, and the rank will be remain n, because these all are independent. Rank of the matrix will be n. Suppose particularly if you take three vectors only, x1, x2, x3, and first column, second column, third column, and it will become 3 by 3 matrix. In that case, rank will be 3 if these all are independent. But if these are dependent, then the determinant is equal to 0 in that case. That is in the form of determinant. But individually, we can also verify whether it is a independent or dependent. If you take each column separately as a vector, x1, x2, and so on, xn, and these all are said to be dependent. If we are able to find some constant lambda 1, lambda 2, lambda 3, and so on, and their linear combination is equal to 0, and all of them are non-zeros, then we say that these are independent. These are dependent, and otherwise, if you find lambda 1, lambda 2, and so on, lambda n, all are zeros, then we say independent. So it is indirectly they are defining a determinant in terms of separating the columns as a vector and defining in another way, because this will lead into the vector spaces. There we will focus more on these vectors. Instead of taking a matrix, they focus on the each column as a vector. And that will also help you to find eigenvalues and eigenvectors also. And there are a lot of applications in the literature of eigenvalues and eigenvectors. One of the example for very simple, like inverse of a matrix, that we already know how to find inverse of a matrix. It's going to be divided by determinant of A, one method, and by using row column operations that we already seen. That also can be A is equal to I into A, and we convert it into identity matrix. A inverse can be calculated. That is one way. And by using eigenvalues, eigenvectors, we can find inverse by using Cayley-Hamilton theorem. So not only that, there is another application. You can also find power of a matrix. Not only that, exponential of a matrix, and many other applications. Not only that, to factorize the matrix. These all will be useful by using eigenvalues and eigenvectors. And here I think we already studied how to find eigenvalues and eigenvectors. However, briefly I recall here. So given matrix, given system of equations can be represented Ax is equal to y as mentioned here. And after simple calculations, it is already mentioned. So finally, we will convert it into homogeneous system of equation. A minus lambda I into x is equal to 0. And as I said, when we have homogeneous system of equations, there is only one option. It is always solution. Always solution is there, and based on the determinant of the coefficient matrix A. Here coefficient matrix is A minus lambda I. If determinant of A minus lambda I is equal to 0, suppose determinant is equal to 0, then it has infinitely many solutions. The determinant of A minus lambda I is not equal to 0, then it has unique solution x is equal to 0, 0, trivial solution. But we have to find here non-trivial solution. In that case, determinant of A minus lambda I should be 0. Then only we will be able to find x. And here the value lambda we call it as eigenvalue, and x we call it as a eigenvector. And once we know how to find the eigenvalue and eigenvector, and using this concept, you can find a lot of applications, not only in mathematics, even image processing and other noising and many other applications also available. So here, the coefficient matrix, determinant of A minus lambda I, we call it as a characteristic polynomial in the form of lambda. And if it is equal to 0, that is determinant of A minus lambda I is equal to 0, then we call it as a characteristic equation, and the roots of this equation or solution of this equation we call it as characteristic roots or eigenvalues. These are we are going to find eigenvalues, and the vector x we call it as eigenvector. So we will see later how to find eigenvalues and eigenvectors and some properties before going to do that one. Eigenvalues. Any square matrix A and its transpose have same eigenvalues. So that is, if you take A matrix or A transpose, both have same eigenvalues. and sum of the eigenvalues will be always equal to the trace of the matrix. Trace of the matrix is nothing but sum of the principal diagonal elements. So diagonal element sum is equal to sum of the eigenvalues. So once after calculating all those things, you can cross check in your exam also that whether eigenvalues are right or wrong. Simply sum of the diagonal elements is equal to sum of the eigenvalues. At the same time, product of the eigenvalues is equal to determinant of the given matrix. If 3 by 3 matrix is given, suppose there will be 3 eigenvalues. It may be repeated or not repeated, unique or distinct, doesn't matter it is. If you take sum of all these eigenvalues, you will get trace of the matrix, and the product of these all eigenvalues is equal to determinant of 3 by 3. So we can cross check in exam also. If it is satisfying these two at least, then we can say those values are correct. If lambda 1, lambda 2, and so on, lambda n are eigenvalues of A, then the remaining values are based on the multiplication or power or inverse that will be applicable. Ka has eigenvalues k into lambda 1, k into lambda 2, and so on. A power m have eigenvalues lambda power m, lambda 2 power m, and so on, lambda n power. A inverse have eigenvalues 1 by lambda 1, lambda 2. Sometimes in examination, they intentionally ask, suppose matrix A has 1, 2, 3 are the eigenvalues, then calculate A inverse eigenvalues. Simply you take 1 by 1, 1 by 2, 1 by 3. So instead of taking inverse of that matrix and finding characteristic equation, characteristic roots, and then that is long process. Simply apply the properties. If A eigenvalues are given, A inverse eigenvalues will be simply reciprocal of the eigenvalues of A. And not only that, even power also. If A eigenvalues are 1, 2, 3, then what are the eigenvalues of A cube? Simply you take 1 cube, 2 cube, 3 cube. So instead of taking A into A, and after the characteristic equation, that is long process. By using these properties, we can shortcut this all those things. For example, if you look at simply 3 by 3 matrix, how to find the eigenvalues, we will see. And then we learn Cayley-Hamilton theorem also. The coefficient matrix here, A minus lambda I, is represented here. A is equal to 6 minus 2, 2, and so on. Matrix is given. And A minus lambda I, the matrix is given. The determinant is equal to 0. And after expansion this, it will end up with a polynomial in lambda, that is minus lambda cube plus 12 lambda square minus 36 lambda plus 32 is equal to 0. So after using you can use calculator, cubic polynomial. We get 3 roots here. Lambda is equal to 2, 2, 8. This we call it as eigenvalues. And Cayley-Hamilton theorem, it is based on the eigenvalues, and it is also one of the very useful theorem, and a lot of applications also available. Using this Cayley-Hamilton theorem, you can find inverse of a matrix. At the same time, you can find a power of a matrix also easily without calculating several means computational cost will be reducing by using Cayley-Hamilton theorem. The statement is very simple. Every square matrix satisfies its own characteristic equation. So that is the statement of Cayley-Hamilton theorem. Hello? Is it okay?
Yes, sir.
Okay.
Fine, sir. Sir, going on. Fine, sir.
Okay. So every square matrix satisfies its own characteristic equation. So that statement is given here. Suppose A is the given matrix. The corresponding characteristic equation is A lambda power n plus A1 into lambda power n minus 1 and so on an. We simply replace lambda with matrix given matrix K. That is the statement of Cayley-Hamilton theorem. That is A power n plus A1 into A power n minus 1 plus A2 into A power n minus 2 and so on. An into last constant. 1 means here identity matrix. In terms of matrices, the last constant is multiplied with identity matrix. This is the statement of Cayley-Hamilton theorem. Using this, we can find inverse of a matrix, power of a matrix, or many other properties of matrices. Simple example is given here. A is given and find A inverse. By using elementary operation, we can easily apply. A is equal to I into A. We have already applied and we have seen how to find inverse of a matrix. And inverse of a matrix by using another method we have already seen earlier. And now we are going to use this method. Earlier means adjoint A divided by det A. That is elementary school method. Now we are going to use Cayley-Hamilton theorem to find inverse of a matrix A. So first to calculate the characteristic equation of the given matrix, like A minus lambda I, determinant is equal to 0, and it end up with a polynomial equation of order 3 as a lambda cube minus 6 lambda square plus 6 lambda minus 11 equal to 0. So as I said earlier, lambda replaced with A. So it will by using Cayley-Hamilton theorem, we have A cube minus 6A square plus 6A minus 11I is equal to 0. Now to find inverse of a matrix, simply multiply A inverse on both sides. So A cube become A square become A, and A become identity matrix because A into A inverse become identity matrix, and I into A inverse become A inverse. So minus A inverse, minus 11 A inverse will come last term, that will take other side, and you can easily find now A inverse. A square can be calculated because A is already given. A square can be calculated by using calculator also. You can do 3 by 3 matrix, A square, A cube, and so on. So A inverse is equal to 1 divided by 11 into A square minus 6A plus 6I. And simple elementary matrix product multiplication and addition and subtraction, which we already seen at initially. So now A inverse is equal to 1 by 11 into 5 minus 1 minus 7 and so on. That is the matrix by using Cayley-Hamilton theorem. So one we have already seen by using a row operation how to find inverse of a matrix. Now Cayley-Hamilton theorem, how to find inverse of a matrix. So one same example can be used to find inverse of a matrix using different methods. And the power of a, as I said, power of a matrix can be also calculated. So if you look back to the same example, if you want to find A cube, so here simply multiply A cube is equal to, already it is there, A cube is equal to 6A square plus 6A minus 11. You take other side, then A cube is equal to plus 6A square minus 6A minus 11I. A square we can already calculated and A is given, I is identity matrix. Simply it is sum of the 3 by 3 matrices. Instead of taking A into A into A, you simply take A square and sum and subtraction of the matrices. So power of this, in general, if you take in general power k or m, a power m, linearly expressible in terms of this lower term. So sometimes you will get a power m. If you take a square is equal to, sometimes you get a, or maybe a power 3 is a power 4 is equal to, sometimes you get a. In that case, it will repeatedly by using Cayley-Hamilton, the calculations will be reduced. And eigenvectors, as I said, a minus lambda I into x is equal to 0. To get a non-trivial solution, the determinant a minus lambda I determinant should be 0. So the x we call it as a eigenvector. So using that vector, we can find there are applications. As I said, one of the application of eigenvectors is image processing or diagonalization of the matrix. You can diagonalize the matrix by using eigenvectors, and this diagonalization will help you to image processing and machine learning. Many applications are there. So this will help you there, and it is not directly useful there, but it will help you to reduce the calculations by using eigenvalues and eigenvectors. Some properties are given here. Eigenvector, the eigenvector of eigenvector x of any matrix is not inactive. So it will be dependent constant multiple of anything that we will get based on the calculation. If lambda 1, lambda 2, and lambda 1 distinct eigenvalues, then we will get distinct eigenvectors, and these are linearly independent. Suppose we have a characteristic equation, cubic polynomial. Suppose cubic polynomial in lambda, we have lambda is equal to 1, 2, 3 eigenvalue. Then the corresponding eigenvectors 1, 2, 3 will be different, and all of these are linearly independent. You can give guarantee for that. But when we have repeated eigenvalues, we cannot give any guarantee whether these are independent or dependent. Since these are independent when these are distinct, we cannot say that when repeated these are dependent, because sometimes repeated eigenvalues may have independent eigenvectors. So we cannot give any guarantee that repeated eigenvalues will give dependent vectors only. No. So that is the case here. When two or more eigenvalues are equal, it may be or may not be possible to get linearly independent eigenvectors corresponding to each eigenvalue. That is the statement. But one way we can give guarantee that if all eigenvalues are independent, all distinct, then corresponding eigenvectors are independent. So two eigenvectors x1 and x2 are called orthogonal. This is well known to vector calculus. Normally we studied in intermediate level, but however, two vectors in general, not only eigenvectors, general vectors. If you take two vectors x1 and x2 are orthogonal if x1 transpose dot x2 is equal to 0. These two are orthogonal. Eigenvectors of symmetric matrix corresponding to different eigenvalues are orthogonal. Normalized form of the vector or unit vector, that is we already know. Normally in vector notation we denote with v cap, that is v bar divided by the modulus of v. Similar like that unit vector is normalized vector in this case. So here normalized vector of 1, 2, 3, 1, 2, 2 will be 1 by 3, 2 by 3, 2 by 3 because here under root 1 square plus 2 square plus 2 square is 3. And the vector space. So all we have discussed about only vectors, and all these vectors form a space, vector space based on some properties. Suppose a set V consisting of some vectors is said to be a vector space with respect to two binary operations, say plus and dot. The plus is from V cross V to V, and the dot is from R cross V to V. Said to be vector space, it should be satisfying some properties. Those properties are given here. However, some of the properties can be ignored by experience and by doing a lot of examples. But initially, as a definition, we have to follow all these steps, means properties. And simpler here, with respect to addition, x plus y is equal to y plus x, that we already know. Two vectors, not only vector, even scalar also. But matrices are completely different in this case. Matrices can be converted into vectors if you take each column, and those we will separate them, make it separate. In this case, x and y are two vectors. So x plus y is equal to y plus x, commutative with respect to addition, that is possible, is true, that is true, that should be satisfied. Sometimes we may find some of the vectors may not be satisfied. In that case, we say the definition is not followed. So x plus y is equal to y plus x plus y plus z is equal to x plus y plus z associated with respect to addition, and there should be additive inverse 0 vector. X plus 0 is equal to 0 plus x is equal to x, that we call it as additive inverse. And there should be additive inverse also for every vector. There should be a opposite vector such that x plus y is equal to 0 or y plus x is equal to 0, that is additive inverse. If x is there, minus x, normally we call it y is equal to minus x. With respect to addition, if we take in general addition, so x minus x is equal to 0. So in this case, y is equal to minus x. So additive inverse should be there for satisfying the vector space. And alpha into x plus y is equal to alpha into x plus alpha into y, where alpha is a scalar and x plus y, x comma y are vectors here. Alpha plus beta into x is equal to alpha into x plus beta into x. And alpha beta is constants here, and x is a vector. So alpha beta into x is equal to alpha into beta into x. That will be also 1 into x is equal to x. 1 is the scalar and x is the vector here. So all these 8 properties should be satisfied to say given set V is a vector space with respect to plus and dot. We will do simple example here. Let x be a non-empty set consisting of all functions f from x to r, and here plus is the sum of the functions, and the dot is a simple product of two functions. That is, this is easily verified by using calculus. So first here in calculus, there are separate function here, limit and continuity functions are the functions and relations. There we have seen that composition of a function, sum of functions, subtraction of functions, and all those things we can easily verify that will form a vector space. And similar to these functions, we can also see that sequences also. Same properties for function f comma g are two functions. Similarly, xn comma yn be two sequences. The same properties is also applicable here also, and we can also say that this is also form a vector space with respect to addition and multiplication. And vector subspace. Subspace is nothing but it is a subset of the vector space, and following the same properties. There we have already seen some 8 properties are following. The 8 properties should be also followed here also. But however, there are some advantages being a subspace that no need to follow all, no need to check all those 8 properties. We simply check a few properties of them. So finally, we can say that that is a subspace of the given vector space. That those properties are here. That W is a non-empty subset of vector space V. V is the main big set. Then W is small subset. Said to be a vector subspace of V. If W itself is a vector space, that should be vector space itself, and it should be satisfying this one. That is, if you check 0 belongs to W, if W1, W2 belongs to W, sum of two vectors from W again belonging to the W, alpha belongs to R, W belongs to W, then alpha W belongs. Instead of checking A properties, we can check these 3 properties. Then we can say this is because the big set itself is a vector space, and we are taking some elements from that, and we will say that this is a subspace. Instead of checking all those properties, we simply check these 3 properties, and if these 3 are satisfied, then we say that that is subspace of the given vector space. And linearly independent, that we already seen earlier. while discussing about the matrices, if you take columns, each column has a vector, and you check whether these are linearly dependent or independent. So in terms of vectors in vector space, if we have v1, v2, and so on, vn are vectors. Suppose V is a vector space and v1, v2, vn, we have elements of this. Those are the vectors. We say that v1, v2, vn are all linearly dependent. If there exists some constants, there we take in lambda 1, lambda 2. Here we take a1, a2, and so on, an, not all zeros, such that the linear combination is equal to 0. If we find any element, any constant a1, a2, and so on, an non-zero, then we say that they are linearly dependent. But we are not able to find any element is 0, all of them are non-zero, if all of them are zeros, a1 0, a2 0, a3 0, and so on, an 0. That is trivial solution, suppose. Then we can say that those are linearly independent. Again, there is a connection between linearly independent, dependent based on the solution of the homogeneous equation. Homogeneous equation has trivial solution or infinitely many solutions. Infinitely many solutions means linearly dependent. Unique solution, trivial solution means linearly independent. The columns of the matrix all are independent. If trivial solution, if non-trivial solution means infinitely many solutions are there, means those are the four columns of the matrix are dependent. So same concept they used here. If it is not dependent, then we say that that is independent. That is, if we not able to find any ai, then we say that that is linearly independent. If all a1, a2, a3, and so on, an zeros, then we say that is linearly independent. For example, you can see two vectors are given 1, 1, minus 3, 2, and we have to check whether these are linearly independent or dependent. So constants a, b, a1, a2, a3, and so on. Normally we take here a, b, the two vectors only a, b we take, and the linear combination of these two vectors, and check whether it has a trivial solution or non-trivial solution. So if you solve this one, we will get a0, b0. Trivial solution it is there. Trivial solution, or we convert it into matrix, find a determinant of this matrix, you get det is equal to 0. Det is equal to non-zero. In that case, we will get rank is equal to 2. So A is equal to 0, B is equal to 0, then we will get linearly independent. If A is non-zero, or maybe B is non-zero, at least one of these two is non-zero, then we say that these are independent. But both are zeros. In this case, we will say linearly independent. And suppose based on this linearly independent, we can decide basis of a vector space. V1, V2, Vn generate V. Generate here it means take any element of V that can be expressed as a linear combination of V1, V2, V3, and so on, Vn. Any element we take general. Suppose V is equal to R square, means space of two elements, x, y. So if you take x, y, that can be expressed as a V1, V2, V3, and so on. So A into V1 plus A, any element you can take, that we call it as a generate. So V1, V2, Vn of V generate V, and moreover these all are independent, then we call it as a basis of V. And there are a lot of comments on basis, means using the basis concept, we will define the vector space very easily, and many properties can be proved easily by using concept of basis. So generating is any element of a given vector space can be expressed as a linear combination of the vectors v1, v2, v3, and so on, vn. That we call it a generation, generate of v, that is L of v. Normally we denote L of v. And moreover, if it is extra linearly independent also, then we say basis of that one. Or we say that constitute or form a basis for vector space V. For example, you can see whether it is linearly independent or not, whether it is generating or not. So that the vector 1, 1 and minus 1, 2 form a basis for R square. R square means x, y, set of all elements of the form x, y, such that x, y belongs to real numbers. So first we check whether these are linearly independent or not, like what we have seen earlier. A into, because there are two vectors only, A into V1 plus B into V2 is equal to 0, and check whether A and B all are zeros or not. So if you solve these two equations, you get A is equal to 0, B is equal to 0, so linearly independent. And we have to check whether it is generating or not. So take any general element from vectors R square, any vector from R square, say S comma T. S comma T is any element from R square, and we have to express this in linear combination of 1, 1 minus 1, 2. So x into 1, 1 plus y into minus 1, 2 is equal to S comma T. We have to find S comma T in terms of x comma y in terms of s comma t. So you can easily express here it is given y is equal to t minus 5 by 3 and x is equal to t minus 5 by 3 plus s. So now we can take any element from R square 2 comma 3. Suppose s is equal to 2, t is equal to 3. Then x comma y easily calculate. If s is equal to 5, t is equal to 3, x comma y easily calculated by using this. So any element of R square can be expressed in terms of 1 comma 1 and minus 1 comma 2. So it generates the vector space R square. Therefore 1 comma 1 minus 1 comma 2 form a basis for R square. So this is the way to check whether given vectors form a basis for vector space V or not. And the number of elements in the basis we call it as dimension of V. And the dimension is the number of elements. If vector space consisting of 200 elements, suppose, and basis form, then 200 elements can be reduced to the number of bases, the number of elements in the basis. So these are some simple theorems that can be easily proved. Let V be a vector space of dimension n, and V1, V2, and so on Vn be linearly independent of V. Then we can simply say that this is a basis, because the dimension of the vector space consisting of maximum n elements, and if you take any n elements and those are linearly independent, we say that is a space because we take the same number of dimension and showing that those are linearly independent. It forms a basis. If E is a vector space of dimension n and W is a subspace and it is also as a dimension n, the big space and the small space have the dimension same, then obviously both are same only, because we are not taking subset of this one big space. So W and V have same dimension, though nothing but those two vector spaces are equal. And a linear map is like a linear function, so that can be easily defined. L is from vector space V to W, and if it should be satisfying two properties, L of u plus V, u and small v are here vectors. So L of u plus V is equal to L of u plus L of V, and L of C comma u is equal to, C is a scalar here, you can take outside from the linear map, C into L of Ux. Simple example in terms of function, if you take f of x is equal to, you can take f of x is equal to 2x, suppose f of x is equal to 3x. In that case, f of x1 plus x2 can be written as 2x1 plus 2x2, and f of 4x is equal to 4 into f of x you can write. So that is a simple linear map. L is equal to V to W, similar to that one. You have to verify only simple these two properties. If these two properties are satisfied, we say that these are linear. And based on when you have a map, obviously we'll discuss about domain and range. And the domain and range, when you have again how many elements are there, that is also matters. So that content we will have here in this case kernel and image of the linear map. And image is as you know that in function terms of function, image of a function, similarly image of a linear map is same. And the set of all elements of V such that f of V is equal to W. We call it as image of that one, like a function. So whatever the values of V mapping to elements in W, those elements if you collect, that will be in the image of the function F. Similarly here also the map F, whatever the elements from V mapping to W elements, those if you collect only those elements, that will form in the image of the F. And we can also verify image of F form a subspace of W, because image is subset of normally W, and it will form a subspace also. And the kernel of F, kernel is the elements, all elements which are mapping to 0. We call it as a kernel. That is set of all V such that f of V is equal to 0. So whatever element you take, if after substituting in the function it will giving 0, then that element belongs to the kernel. Again, the kernel form a subspace of V. So here kernel is subset of V and image is subset of W. That is already known. V is the domain and W is the codomain, and image is the subset of codomain, and the kernel is subset of domain. And moreover, this will form a subspace of W and V respectively. And the dimension of V is distributed linearly to both the kernel and the image. Equal means not equal means completely distributed. If the dimension of V is equal to 10, suppose, then it may be dimension of kernel of 3 or 7 or 6 or 4, like that. So dimension of V vector space can be written as dimension of kernel of V plus dimension of image of L. So this is one of the important theorems in vector spaces, and this can be obtained from the reference books that I mentioned already in the list of the references. You can go through it, and this is one of the important theorems. Dimension of V is direct sum of kernel dimension of kernel L and the dimension of image L. And we will go through the simple example. Suppose L is R cube to R, so input will be x, y, z, three values because it is R cube, and output will be R, that is 3x minus 2y plus z. This is a map, and we can express this in terms of matrices also. Suppose if you take right hand side 3x minus 2y plus z, if you take only the coefficient as a vector, A is equal to 3 minus 2, 1, the coefficient of x, y and z, 3 minus 2, 1. Then L of x, capital X will be the vector x, y, z. Then the same map L of x, y, z is equal to 3x minus 2y plus z can be expressed in terms of A and capital X. L of x is equal to x dot A or A dot x. That will be the same as 3x minus 2y plus z. Now, the kernel is nothing but the solution, the elements which are mapping to 0. So 3x minus 2y plus z is equal to 0. So now we have to find the values of x, y, z which making 0. So it will be from again it is system of linear equation, one equation and three unknowns. So in this case we will have infinitely many solutions. So we can find kernel of the map R cube to R, which is defined by L of x, y, z is equal to 3x minus 2y plus z. So we can generalize this in the, instead of 3, we take n. L from Rn to R, and L of x is equal to A dot x. There we have A is equal to 3 here, vector of size 3, but here vector of size n we will take. So simply generalize 3 to n here in this case. And we simply take a product of this, the kernel will be taking simply dot product you are taking. That is, when you are taking dot product is equal to 0, then we say that those vectors are perpendicular. So here 3x minus 2y plus z is equal to 0. That is nothing but x dot A should be 0. So x is x, y, z, and A is a vector 3 minus 2, 1. Dot product should be 0. In that case, x and A should be perpendicular. So same thing it is mentioned here. And the matrix associated with a linear map. So here we can see previous slide. You can see LA from Rn to R. Input will be nth vector of size n, but output will be vector of size 1, that is scalar only we will get. But output also not a scalar. If it is also a vector, then that will be converting into a matrix. Instead of we will get here vector A is equal to 3 comma minus 2 comma 1. Here we will get a matrix because the output is not a scalar. The output is of a vector of size m. In that case, we will get matrix of n by m. So that is a generalization again of a previous one. So once it is clear, the example one, the other one converting into n, and the right output also instead of scalar, if we take m vector, then it will be giving matrix. Simple example here it is, V is a vector from V to V, where V is R cube to R cube. Then we will get a 3 by 3 matrix in this case. And the map is defined, L of V1 is equal to 2 into V1 minus V2. L of V2 is equal to V1 plus V2 minus 4 into V3. L of V3 is equal to 5V1 plus 4V2 plus 2V3. And we collect simply coefficients of this one, and we take transpose of this one, that will represent this one. So that is the matrix representation of a linear map from V to V, and which is defined by here simple equation. So that is about the linear maps and linear spaces, vector spaces, and linear equations, and before that matrices, and before that brief introduction about the definitions of the matrix. So there we have already seen system of equations. There inconsistent systems. There we will not be able to find the solution by using analytical methods. In that case, we will come to the numerical methods where we will find approximate solution when we are not able to find exact solution. So we'll start with scalar equations, system of scalar, not where we've taken system of equation, now we take scalar equation. And there we take a linear equation, now we will take transcendental equation. So the difference between these two equations, linear equation is nothing but it is consistent power 1. Transcendental equation is a combination of anything, that is a trigonometric or logarithmic or exponential or maybe a polynomial or maybe anything. Combination if you take, that form a transcendental equation. And if a combination of all these three is equal to 0, we call it equation, that is f of x is equal to 0, that is we call transcendental equation. There are several methods to find a solution of the equation, and however we will focus only few of them which are included in our module. So the first one is bisection method or Boltzmann method. Bisection method is it will bisect the given interval. By means here 2. So it will divide the interval into two parts. So the main formula here is xn is equal to 1 by 2 into xn a plus b. First, suppose interval a comma b is given. First iteration is a plus b divided by 2. That is middle of the point, average of the point, whatever it is, the middle point. So the whole interval is divided into two parts. And we will search between among these two parts, one part 2, where the root or solution is existing. And by using fundamental theorem of calculus, you can say that it has a root or solution only when f of a dot f of b less than 0. That is, f of a and f of b have opposite sign. Suppose f of a is positive and f of b should be negative, or f of a is negative, then f of b should be positive. Then only there is a root between a and b. So that is the theorem. So now first we will check whether given interval is satisfying this condition or not. That is f of a dot f of b less than or 0 or not. So once calculating this first iteration, x1 is equal to a plus b by 2, and we check this f of x1 0, then that is exact root, that is required answer. If it is not, then check whether it is positive or negative. Based on that, we will decide whether the root is lying in the first half or second half. If it is first half, again we will do the same process. Again we will bisect that one and we will check the same process, repeat this until we will get the required answer. Simple example, x into sin x plus cos x equal to 0. Between 2 comma 3 using bisection method. So f of x is equal to x into sin x plus cos x, and for a is equal to 2, b is equal to 3. Interval is given a comma b, 2 comma 3 here it is. We substitute these two values in the given function, check whether one should be positive, other should be negative. Whatever it is, 2 or 3 or 2, 3 or 2, no matter it is. If one is positive, the other one should be negative, then only there is a root between a and b. So it is satisfying one is positive, 1.4. The other one is negative, minus 0.5. So there is a root between 2 and 3. The first iteration is x1 is equal to a plus b by 2. That is 2 plus 3 divided by 2.5, the middle. So 2 comma 3 middle is 2.5. So we divide this one. We check again 2 comma 2.5 or maybe 2.5 comma 3. Among these two, where the root is lying. Again, we substitute these two values and check this less than 0 or greater than 0. And f of 2.5 and f of 3 less than 0. So there is a root between 2.5 and 3. And again, we bisect this one. Average of these two, 2.5 plus 3 divided by 2, that is 2.75. Again, we will check either the first half or second half. We ignore the previous part. Now onwards, we will decrease. Each step, the whole interval is bisecting. Suppose if you have 100 points, suppose. So first step will make it 50 points, next point 25 points, next into 12.5 and so on. It will keep on bisecting. It will divide, making a half of that each of the step. So after sixth approximation root, we will get six iterations. We have 2.79 and so on. And there is a stopping criteria. If f of approximate root is almost 0, you can stop this process, or maybe the up to 4 decimal places are correct. That is fifth approximate root and fifth approximate root. Both are almost the same. Then we can stop this process, or maybe you can take a absolute error based on the requirement. We will stop this process and then final approximate root will be collecting from the method. So this is first bisection method. The other one is Newton-Raphson method. The Newton-Raphson method, the formula in this case is n plus 1 is equal to xn minus f of xn divided by f dash of xn. So function values are there and the derivative also you have to calculate. The difference between previous method and this method is previous method will take lot of iterations to get the approximate root, but here we will get fast converging, that is less number of iterations are required. However, there is a lot of difference again. The previous method, bisection method, will give guarantee that there is a root, and we will find after maybe 100 iteration or 200 iteration or 250 iterations, whatever it is. But guarantee we can say that root can be calculated. But Newton-Raphson method, we cannot give 100% guarantee that we can find root. Sometimes it may not be give exact root means close to the exact root, because if f dash of xn becomes 0, denominator becomes 0. In that case, this method cannot be applicable. So the drawback of this Newton-Raphson method is when the derivative of f at x0 or x1, x2 and so on, it should not be 0. Then only it will be applicable and it will converge fast. And for example, you can see that f of x is given here, x cube minus 2x minus 5. And initially we can take whatever the approximate root, either 2 or 2.5, based on the requirement we can take. And since the formula containing f derivative also, so find f dash of x. So x cube minus 2x minus 5 derivative is 3x square minus 2. We substitute 2 there also. First iteration is x naught minus f of x naught divided by f dash of x naught. 2.1 we will get first iteration. Again 2.1 we take it as input for the second iteration and repeat the same process. We will get 2.09. And 2.09 we take as the input again and repeat the same process. F of 2.09, f dash of 2.09, and substitute here x1 minus f dash of x1 divided by f dash of x1. To calculate, we will get approximate root. And finally, after 3 iterations, we will get 2.09. We can observe that here x2 and x3 correct up to 4 decimal places. 4 decimal places is 0.0945, here 0.0945. 4 decimal places are correct. That is the stopping criteria for this problem. So we can stop after this. Or maybe f of f of x2 is equal to almost 0. Some value into 10 power minus 6 or 10 power minus 3, something that is also one of the stopping criteria. But here we have 4 decimal places are correct, so we can stop this process. And a numerical differentiation. So this will help us to calculate derivative of the function. Sometimes when you are not able to find a derivative or it is not differentiable function, but approximately we can calculate that one. And this will also help us to calculate the initial value problem approximately when there is no solution of given a initial value problem or boundary value problem, but at least we can find approximate solution. So numerical differentiation is help us to find approximate value of the derivative function at a given point. And there are 2 methods here, derivatives using Newton forward difference formula. Other one is derivatives using Newton backward difference formula. The formula can be derived easily by using a Taylor's expansion. After doing those expansions, finally we get formula here f of x is equal to f of x naught plus x minus x naught and so on. And the nth term we have x minus x naught, x minus x1 and so on, x minus xn minus 1 into delta power n f naught divided by n factorial into h power n, where h is the space. Suppose we have some points xi and f of xi. Then in short, we can say x comma y, xi comma yi. So f of xi denoted as yi. Then x comma y points are given, and first point, second point, third point, and so on. The space between first point, second point, and the second point, third point, that denoted by h here. Equispatial, that is 0, 2, 4, 6, 8, and so on. That is equispatial. In this case, h is equal to 2. Now, when the function can be represented in this way, derivative of this function can be calculated at x naught. Simply derivative on both sides and substitute x naught, and simplifying we will get f dash of x naught is equal to 1 by h into delta f of 0 minus 1 by 2 delta square f naught and so on. And the second derivative, again differentiating this and substitute x is equal to x naught, we will get the second derivative and so on. We can find up to n derivatives based on the requirement. This is by Newton forward difference formula. And if you ignore the higher order their power, delta power 2, delta power 3, delta power 4 and so on, if you ignore, then we will get f dash and f double dash at x naught. In general point xk also you can calculate any point. And Newton backward difference formula, it is exactly same as that one. By using Taylor series expansion, we get only the formula there we use delta, we use here del. And table also the way of calculating delta and del also different, that we will see with a simple example. And f of x is representing by using Newton's backward difference formula is here, and the derivative on both sides again, and substitute x is equal to xn. Earlier we substitute x is equal to x naught, now we substitute x is equal to xn. And earlier we denote h here, we denote as space is equal to first last value here, so 0. Earlier x naught space was 0. The initial value only we taken. So first derivative we have here and second derivative. Similarly, if you ignore higher power, then we will get same as in the forward differences. Simple example, you can say find the f dash of 3 and f double dash of 3. And table is given, x values are given 3.0, 3.2, 3.4, 3.6 and so on, 4.0. Here h is equal to the equispaced here. H is nothing but x1, x0 is 3, x1 is 3.2, x2 is 3.4 and so on. The space between x values, that is 0.2. And f of x is given if you denote yi, y1, y2, y3 and so on. You can simple it is. And the table here, forward difference table. X values are given 3, 3.2, 3.4 and so on up to 4. And y values or f of x values are given second row. So that is placed here second column. And delta f is obtained simply second value, that is y1 minus y0. Here 10.03 minus 40 minus 14. And delta y second value obtained 5.296 minus 10.03. And the other values likewise, we will take second value minus first value and we place in the middle of these two values, because that indicating that the difference of these two we put the middle of this one and keep on doing here until we get a single value at the bottom. Or we can also identify how many values are given. So 1, 2, 3, 4, 5, 6. 6 values are given in the table. So we will get maximum of up to del power 5. So n is equal to suppose we have 6 minus 1, 5. Del power 5 we will get. So finally we will get one value. Now from here, from table, delta f, delta square f, delta cube f, delta power 4 f, delta. The first values, first top values that will indicating delta f naught, delta square f naught, delta cube f naught, delta power 4 f naught and so on. And the second value is delta f1, delta square f2 and so on, it will indicate. If you take from bottom, it will indicating del f naught, del fn, del square fn, del cube fn and so on. That will come backward. So for forward, we take top values only. So f dash of x naught is equal to, where x naught is equal to 3. So x naught is equal to 3 here. So we substitute here. X naught is equal to f dash of 3 and h is equal to, as equispaced value, 0.2. And delta f naught, first value, that is 3.96. 1 by 2 into del square, that is 0.76, and so on. Substitute and use calculator, we will get f dash of 3. So without using any derivative, simply we are using simple calculations, and the derivative of the function at 3 is calculated. Even we don't know the function also. We know only the function values at different points, and we calculated derivative of the function at 3. Similarly, second derivative also calculated by using Newton forward difference formula. So that is also given in the previous slide main formula, simply substituted here up to delta power 5. And backward example, find f dash of 3 by using Newton's backward difference formula. 1, 1.5, 2, 2.53 is given. Here equispaced and h is equal to 0.5. And the same, the formation of table is remains same, but collecting the values from the table is different. There we taken forward from top to values, but here we take from bottom values. So del fn, instead of there delta f naught, we take del fn, that is last value 3.1. 125, 2.25, 0.75, and the last value is 0. We substitute this value, we get f dash of 3. So these are the numerical differentiation of given function. Even you don't know the function, but we have the values only, and the derivative can be calculated by using Newton forward and backward differentiation. And similarly, numerical integration also. So to find integration, so finding integration of a function is very difficult. No, it is not simple always. So in that case, even sometimes it is very impossible to find an analytic solution of the integral value. So in that case, we will find approximate value by using numerical integration. There are some certain rules or methods to find integration of a given function. So mainly we have trapezoidal rule, Simpson one-turn rule, and Simpson 3/8 rule. So we learn all these three methods. We recall all these three. Trapezoidal rule that can be applied easily, and easy remind you or recall you how to remember very easily. Integral a to b f of x dx, and it is the first method. So h by 2, first value and the last value, write together one set, f of x naught plus f of n. The remaining all values multiply with 2. So h by 2 is equal to f of x naught plus 2 into the all middle values and the last value of x1. 2 into f of x1 plus f of x2 and so on, f of xn minus 1 plus f of xn. So this is a simple way to remember. And all data will be given. F of x will be given, f of x naught will be given, x1 will be given, and so on. N value will be given, h value will be given. Only we have to simply substitute here without using any integration or derivative. The integral value can be calculated. Simple application of numerical integration is finding a distance traveled by an objective. Suppose velocity of a particle is given, and we have to find total distance traveled by the particle in 20 seconds. It is a simple application, physics from the physics, but we don't have the equation of the particle, but we have only the calculated value from observed values. So t time is given and velocity is given, but we have to calculate distance travel in 20 seconds. So we already know that velocity is equal to ds by dt, and so converting this into, we'll get integral s is equal to integral of v, and we have to find up to 20 seconds, so 0 to 20 v into d. And 0, the time interval is given 0 to 4 and so on. So time interval here h is equal to 2, and function values are given 0, 16, 29, 40 and so on. 3 0, and s is equal to, that is distance traveled by the particle. S is equal to the formula h by 2, first value and the last value write one time, that is 0 plus 0. The middle all two values 16, 29, 40 and so on up to 3 multiply with 2. Sum multiply with 2. So 0 plus 0 plus 2 into sum of all these middle values, and use calculator where h is equal to 2. So 2 by 2, that will be 1, and simple calculation sum of the values, that will give 486 feet. So this is the trapezoidal rule by using a numerical integration, very simple to do. The other one is Simpson one-third rule. So the difference between trapezoidal rule and Simpson one-third rule is there h by 2, here we have h by 3. So that we call it the coefficient of h is 1 by 3 in this case, and it is also easy to remember. The first function value and the last function value remains again add up only coefficient is 1, f of x naught plus f of xn. The middle values, even numbers are multiplied with 2 and the odd numbers are multiplied with 4. So in the function values table, earlier we have seen first value, last value sum up, and middle values are multiplied by 2. Here first value, last value add up, and even numbers are multiplied with 2 and the odd numbers are multiplied with 4. You see simple example, same example, same application, but we are using Simpson one-third rule. So s is equal to integral 0 to 20 p into dt. So formula s is equal to h by 3, h is equal to 2, again 2 by 3. First value is 0, last value. V value means here v, velocity in this case, the function value. 0 plus 0, and even numbers are multiplied with 2. Even numbers means second value. First year, second value, fourth value, sixth value, eighth and 10th value, and so on. Multiplied with 2. Odd numbers, third position, fifth position, seventh position, ninth position are multiplied with 4. So you can observe here, it is already mentioned 2 by 3 into 0 plus 4 into 16 plus 40 plus 51 and so on, plus 2 into even numbers, 29, 0, 1, 2, 3 and so on. 29 plus 46 plus 13 and so on. So it will be 494.667 feet by using Simpson one-third rule. Similar to this one, we have Simpson 3 by 8 rule. So here the coefficient of h is 3 by 8. So 3 by 8, and the function value, the formula also very simple again. First value and the last value again repeat only one time. And here, hello, is it okay, sir?
Yes, sir, it's fine, sir. Going on.
Okay. So going to finish, sir. So it is also similar to Simpson one-third rule. You can see here. And the examples, we can take same example as exercise, you can practice and we can try and we can get the output, we will get almost same answer. And numerical solutions of ODE. So here we are going to solve initial value problems. Initial value problems, sometimes it is very easy to solve. However, there are some other non-linear equations which cannot be solved easily. Even that look like simple also, but we cannot able to find analytical solution. In that case, we apply numerical solution. And there are different methods. Mainly we have Euler's method, modified Euler method, and Runge-Kutta method. So Euler method, first one, Euler has introduced a method yi plus 1 equal to yi plus h into f of xi yi. Here h value is given as usual what we have done earlier. Y dash is equal to f of x comma y. Right hand side function is given, and initial value y of x not equal to b naught is given. So from this data, we can substitute all the data. And ALR has modified this formula later on, and he has found a little more appropriated, give a more approximate solution to the exact solution. So that was given by the LR again, that we call it as a modified LR method, and it is given here. yi plus 1 equal to yi, which is actually part of that LR first method, what is initial method, that is become a part of this one. And that will be taking as input, and then we repeat this process by using these two combination of LR method and modified LR method. I think it will be more simple if you look at the simple example. Solve the following initial value problem using modified LR method. With h is equal to 0.1, h is given, and 0 to 0.3 is given, y dash is equal to y plus x or x plus y, and y of 0 is equal to 1. In this case, x naught is equal to 0, y naught is equal to 1, and f of x comma y is equal to x plus y. The exact solution is given just to compare whether our approximate solution is close to the exact solution or not, just to compare and verify that one they given. So applying this modified LR method, formula is given in previous slide. We simply recall here I is equal to 0 first is, then we will get y1 if I is equal to 0. So in that case, we will get yi plus 0.1 f of xi plus 0.05, yi plus 0.05 f of xi yi. So x0 is equal to 0, y0 is equal to 5. It is collected from the given data. So I is equal to 0, we will get y1. y1 means h is equal to 0.1. So the first value y of 0.1. If I is equal to 1, we will get y2. That will be 0. At y at 0.2. And I is equal to 2, we will get y3. That will be y of 0.3. So 3 iterations we have to do because there are x belonging to 0 to 0.3 and h is equal to 0.1. So the first iteration y of 0.1 by using formula and substituting all the input data, we will get 1.11. And to take this as an input for the second iteration again, x1 is equal to 0.1, y1 is equal to 1.11, and y1 of dash is equal to f1, that is y1 plus x1, and the data we have already x1 and y1, that is 1.21, and y of 0.2 is nothing but I is equal to 1, that is y2, and again repeats the same process and end up with y2 value that is equal to 1.24, and take this as input for the third iteration again. So third iteration we have 1.39. So first iteration, second iteration, third iteration calculated. Exact answer is also given at the initial stage, that is y of x is equal to 2 into e power x minus 1. So we compare these two whether our numerical method is give approximately close to the exact solution or not. At 0.1, numerical solution is 1.11, we already done, and exact solution is 1.1103, almost close. And 0.2 is 1.242, here 2428, almost is also 0.3, 1.398, 1.3989. So it is also almost close. So the value of h will decide how much close or how much far from the exact solution. So the numerical method, whatever introduced by the ALR, that will be more appropriate to find approximate solution. After that, we have one more final method that is more that after this LR method. They have introduced the Runge-Kutta method of order 4. This will give more appropriate than that LR modified method also, as that was the earlier initial stage. So people were used to follow that one. That is also, but later on, many researchers and teachers and many scientists have introduced different type of Runge-Kutta's order, 4th order, 6th order, 7th order. However, as a basic and important method for engineers is Runge-Kutta 4th order method. The formula is here given to find a solution of initial value problem. There are total 5 steps. One is main step, that is consisting of yi plus 1 equal to yi plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4. K1, K2, K3 are given here. We have to calculate all those K1, K2, K3, K4 and we substitute in the main step to get the first approval. It will take little long time, but we can also create algorithm for this either in MATLAB or Mathematica or Python, because formula is fixed here. Input is also given data, and it will calculate as per the formula given here. Create your algorithm based on this formula and take one example. Say this example only, y dash is equal to x cube plus y. Take f of x comma y is equal to x cube plus 1, and initial data x0 is equal to 0 and y0 is equal to 2, and compute y of 0 2, y of 0 4, y of 0 6 by using this one. You can create your own algorithm by using these formulas, either whatever the programming language you are comfortable, either in Python, C, C++, Java, or anything. Not only that, even with mathematical tools also you can use Mathematica or Maple or Singular software, any other software. And instead of doing manual calculation, this will make you your thinking ability, how you are substituting all those things. And programming language you will create whether you are able to create your own algorithm or not. So here manual calculations is exactly similar to the ALR modified method, but the calculation process is usually different. As for the formula, you have to substitute and you have to verify whether you are getting approximate solution correctly or not. And since we have to calculate y of 0.2, y of 0.4, y of 0.6, 3 iterations are required. The first iteration at 0.2, we get y1 is equal to y0 plus 1, y0 plus 1 by 6 into k1 plus 2, k2 plus 2, k3, k4. K1, k2, k3, k4 are already calculated here. So simply substitute here and you get 2.44. And take this as the input again and go for second iteration. And there we will get approximate solution 2.9905. Again, we take this as input for third iteration and we do the same process and we will end up with 3.68. So finally, we have approximate solution of initial value problem at y 0.2, y equal to 0.4, y at 0.6 value for calculation. And these are the references. These books are available, soft copy. If anyone is interested, I can share all these books. It is available with me, or I can share with organizers so that you can share with your students also. Thank you all for your attention.
Yeah, dear students, if you have any questions, please use chat box. Sir, I think nobody is giving any questions. So, sir, please provide your mail ID so that if anybody wants to interact with you, they can directly contact you.
Yeah, my email
Yes, sir.
ID is T
Yes, sir.
_Srinivasarao at av.anuprabha.
Yes, sir.
Anytime they can
Students,
contact, anytime they can write.
yeah, if you want to get any information from sir, you can directly contact him on this mail ID. And sir, I would like to extend my gratitude and a deep sense of appreciation as we come to the close of this insightful talk. First and foremost, I would like to express my sincere thanks to our esteemed speaker, Dr. Srinivasarao Tota, who has graced us with his wealth of knowledge and expertise. Your presentation has been illuminating, offering valuable insights into the intricacies of the concepts matrix algebra and computational methods. A special note of appreciation goes to our attendees, the students. Their participation and enthusiasm have added immeasurable value to the discussions. And I also extend heartfelt thanks to our management, Vice Chancellor and Head of the Department, whose support has been pivotal in making this talk possible. Your commitment to promoting educational excellence is truly inspiring. And then to all the participants, you have joined from various classes. Your presence here has enriched the dialogue and fostered a sense of collaboration. We hope the knowledge shared today will definitely serve a positive change in you. Wishing all success in our academic pursuits and endeavors. Sir, Srinivas, really thank you. You have spent a lot of precious time with us.
Thank you, sir.
Though you are
Thank you
in
for calling me.
holidays, yeah, you spent your time for our students. And definitely we require this kind of cooperation even in future.
Yeah, sure.
Thank you very much, sir.
Thank you, sir.
And students,
Ravindra sir is telling something.
Yeah, Srinivas sir, thank you, sir. Thank you very much.
the students have shared a feedback link in the chat box. Please try to fill it. After filling the feedback, you'll get a certificate on your mail. And after filling the feedback, you can just leave the meeting. And Ravinder sir, I'm concluding this.
Okay, sir. Srinivas sir. Thank you
Okay,
very
sir.
much.
Thank you. Yeah, once again, thank you for giving this opportunity. Thank you all.
Right, sir. Srinivas sir,
Okay.
if you have any work, you can leave. I'll just wait
Yeah.
for a few minutes so that students fill the feedback.
Yeah. Okay. Bye to all.
Thank you, sir.